Hello, everyone. Welcome back for another edition of our AMP Calgary chapter webinar program. I'm your host, Brett Johnson. So today I have the great privilege of welcoming Tim Alleyne from Suncor Energy to our webinar program. Tim is an electrical and mechanical engineer who has worked for many of the major oil companies in the world. His experience on storage tanks stems from working in the field on tank cleaning, operations, inspection, repair, demolition, and construction. He's a certified API 653 inspector and has worked on riveted tanks, internal floating roof tanks, and external floating roof tanks. Recently, he has worked on a robotic tank inspection program and with other advanced inspection technologies that has helped the industry save on turnaround time and reduce time to market. Tim, thank you so much for joining me today. You know, it's a real pleasure to have you come on our platform here.
Hey, thank you so much, Brett. It's thanks for having me. I appreciate it, and it's nice to know that there's a few people that are interested in tanks. So thank you for having me today.
Awesome. So what are you going to talk about today here?
So the idea of this is really to give people an understanding of storage tanks, what they're about. I mean, the real basics, right? So a lot of people see storage tanks in the industry. What's the difference between that and, a can of Coke, right? So basically this whole idea is sort of for those who don't know anything about it, try to give you a bit of a understanding of how we see it in the industry and what we do and how these things work. So hopefully it's sort of a session to get people a bit of an awareness of what storage tanks are and the fact that they're so important in our industry, really what keep us going. Yeah, pretty much that's pretty much what I'd like to cover. Yeah.
I mean, that sounds super exciting, Tim. I'm really looking forward to it. I think this will be a really good talk for, even for like people like me who know very little about tanks on there. I think I'm going to really appreciate getting this good little one-on-one here so that I know how to not talk so ignorant about tanks around facility people around. So before we jump into that, we need to start and acknowledge our sponsors, because really none of what AMP Calgary can do would be possible without our annual sponsors. Their contributions allow us to be able to continue to provide this webinar series for membership at no charge. So today I'd like to highlight one of our gold sponsors, Stantec. So Stantec believes that integrity begins with people. Their team of specialists have the technical and field experience to provide practical and creative solutions to ensure integrity of your assets. Their goal is to deliver safe, reliable, and regulatory compliant solutions to the oil and gas industries. Experts include inline inspection specialists and NACE accredited corrosion, cathodic protection, and coating professionals. They aim to work collaboratively to provide comprehensive integrity strategies for their clients. Integrity just isn't a job for Stantec, it's part of who they are. And of course, to all the other sponsors are a huge reason why we can do what we do. Our sponsors help fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to our industry and the next generation of engineers. To each one of our sponsors, we sincerely thank you for your continued support. So if you haven't had a chance yet to check out our YouTube channel, please go to our website at nacecalgary.ca, where you can find the direct link to our channel and all our past presentations. So Tim's going to be giving his presentation live. Be sure to stick around after the presentation as we move into a live Q&A session. Please submit your questions in your Zoom client by clicking the Q&A button on the screen down at the bottom there. And then from there, I'll be sure to go and ask your question to Tim. So without further ado, Tim, go ahead, share your screen and take it away.
So what we're going to talk about today is atmospheric storage tanks. So from tank design, capacity, levels, types of tanks, floating roofs, soil conditions and tank foundations, tank floor, shell, miscellaneous tank components, common problems we have, inspection requirements and mitigation, and then some Q&A. So basically the first thing I'd like to say is, as you see, this is basically, it's based on all the industry, right? So wherever I worked and I've accumulated all of this over the years. And I'm trying to one of my biggest goals is to try and share this knowledge with the community. There's lots of lessons learned that I've had. I've been in tanks since about when I was 16 years old. I'm only 18, I wish. No, so I'm older than that. I won't tell you how much, just because, yeah, probably laugh at me, but so I've been doing this for a long time. So I started off in my career, I was working at a smaller terminal. It was a chemical plant, so we were storing lots of xylene, all the aromatics you could find, and so in a lot of different storage tanks, carbon steel, stainless steel. So it was interesting, really, to be exposed to that, how we operate them, how we clean them. For example, cleaning an ethanol tank is very different than cleaning an asphalt tank. So that was some pretty interesting learnings from that. So those of you who have seen those products could understand probably there's some particularities about them. So that, and then we eventually got into a lot of biofuels in the industry. And when that started, and sort of how we had to think about storage requirements for that. So there's lots of interesting things, but the first thing before we go into all of that is really to just say, what is a tank? So then I will extrapolate, and I'll speak more to the slides than what you'll probably see on the slides, because I like to talk and I like to, things come up on the fly. So that's how I like to present this. So we have atmospheric storage tanks, API standard, which is American Petroleum Institute. And essentially, back in the 20s and 30s, the first one was in the 30s, where they came up with the first API regulation. They realized, as you can see with pictures here, that's an interesting concept with a wooden tank and some oil in there and some straps. Going from that, they said, hey, I think we have to improve on the situation. So what they did was they took a lot of industry experts, mechanical engineers, all different types of engineers, and they came up with the best practices, right? Which eventually became code. Now, it's not just in America, they also did that in Europe, all over the world, really, started to try to align with some standards. So there's some variances across the world as far as how tanks are built, the types of materials that we're selecting, and all of the standards. There's some slight variances, but they're all pretty much the same thing. At the end of the day, you want to store your product safely, right, without damage to the environment. You also want to make sure that you maintain the product as well, and the safety of individuals, right? So you want to make sure that, if people are going to be doing anything with the tanks, that it's structurally sound, it's able to support people, able to support the operation, and it lasts, it has a longevity to it, right, for the business as well. So there's all of these things to take into consideration. So going with that, we have the different types of tanks that we'll see here. So you have a cylindrical flat bottom tank. So really what it is obviously it's a cylinder, and essentially that was the most efficient design that they could use, because if you look at a sphere, it can hold pressures much easier than the cylinder. So the other part of it is how it's built and where it sits. There's people might say, well, what's the best shape and how do we approach this? So a lot of times it comes down to cost, constructability, land usage. All of these things come into play. So over the years, they realized that this was the best shape for the storage of products. It's uniformly supported. You have cone up and cone down as well, and cone up meaning that just the floor of that tank inside is shaped upwards to the center, and when it's cone down, it's shaped downwards to the center. And we'll speak a little bit more about that later and for the reason of that. Obviously, uniformly supported, as I just said. Design temperature up to 200 F. Lower temperature not to exceed lowest day average temperature plus 15 degrees F. This is area dependent, right? So, and that's really for brittle fracture, right? So brittle fracture, as we all know, it happens quickly, and it's usually with the first load, right? So we want to make sure we avoid that, and the way to do that is to have the right design temperature, and then from that you have the right materials, thicknesses, and so on and so forth. They come in different sizes and shape, mostly cylindrical, as I was mentioning, just easier to construct. So then when you look at tank design, right? So you think, okay, geez, it seems complicated. What is going on here? How do we do this? So you think of the specs, right? So the first thing you think about is what design code are we going to follow, right? API 650 in North America is one we follow, but it also depends on the tank, because you could have a very small tank and that might not necessarily be covered by that code. You might use something like Steel Tank Institute. You might use something like, well, ULC tanks, right? They have Canadian standards. There's various standards, right? It's sometimes it's a choice and sometimes it isn't. It also depends on the locality. They might have other codes and standards. So what we like to do is we like to go the most strict one, right? So you have company policy, you have standards that are in the industry. You have to select the ones that make the most sense, but obviously the ones that are most safe, the ones that are going to allow you to store this, given what you're looking for, right? So then you go, okay, we know what codes and standards we have to design to. A lot of the times what you'll have to look at is obviously what your existing permits are if you're on a brown field, and if you're on a green field, what that might require as far as permitting is concerned. So there's going to be some back and forth with some experts, and you'll talk about what type of soil conditions you have and what you store already, or if you haven't stored anything already, what that's going to look like, where you are, right, as far as in the community, what the risk is to the community as well. So a lot of these things will come up, and so you'll be building and doing things accordingly to make sure you mitigate that risk. Then, okay, so type of construction, you'll see here fixed roof, what we call fixed roof. So that fixed roof basically is a roof on the tank. It doesn't move, it's there, it's supporting, and it's protecting the internals. You'll see in some areas where there's water tanks that do not have a fixed roof, open tanks. That happens. It's in the industry and is still around. You'll see internal floating roofs, which is basically a roof on the inside with a fixed roof that moves up and down. You'll see external floating roof, which is exactly that. It does not have a fixed roof on top. It has a moving external floating roof, right? Then you go, okay, well, we know sort of what we want to do, and I'll get to more why we select what we select later on in the slides, but you'll see capacity and dimensions. So basically your volume, right? So how do we get the volume that we're looking for? And you say, well, what am I actually looking for? You have to look at the business case and say, well, I have throughput going through this tank. How much do I want to do that? That's one thing you look at. So it's really a buffer for the industry to be able to say, well, it could come in by vessel, rail car, trucks. You need some sort of buffer because you can imagine you have to transload. And what I mean by transloading is going from truck to truck, which is a bit more risky. Again, you have to look at, the volumes going from one to the other. So this tank allows you to be able to do that, buffer it safely, put all the level fill, all the protections as per API 2350, the fire protection. All of this happens in that buffer, and you can also do mixing in the tank because that might be a requirement. You might have to heat the product because sometimes you have product going, thousands of miles really, and it has to maintain a temperature, or you have to bring it up to a temperature, right? Sometimes for viscosity, product quality, all of these different things. That's where a tank comes into play. And then you look at what type of foundation is required. Well, what do we have currently? What does our foundation look like right now? How do we make sure that it's uniform? How do we make sure that over the years it does not move, or it moves very little as per what's required in API or other standards? And why we say that is because if you take a cylinder like a can and you put it on an uneven surface and you were somehow able to put force on there, enough force, you'd see that the can would warp, its shape would change. That change can happen and induce force, stress on the shell, stress on the welding, and it'll typically break your weakest connection, right? So that's why we consider making sure that it's uniform, right? Very important, as well as corrosion, right? So as you know, if it's carbon steel or stainless steel or what have you, there's obviously issues, right? So there's damage mechanisms that happen. So we try to eliminate or mitigate that, right? So there's many ways that we'll talk about that later on. Design liquid level. So that goes back to the volume. So once you have a business case and understanding exactly of how much you want to fill, then there's a design liquid level, right? So you can imagine how the density of the product is going to be pushing with gravity against that shell. So there's going to be some what we call hoop stress. And really all it is really stress on the shell, right? And you'll have stress on the bottom as well. You'll also have stress from the product within that vaporizes. So all of these things have to be taken into consideration. And one little thing that, you know, we talk about liquids and flowing in pipelines and entering in tanks and all these different things. A lot of the times people forget that there's expansion that happens in our liquids in the industry. There's a rule of thumb of 2% a lot of the times. We used to use that as a rule of thumb back in the day. And essentially what you have is you have API has a list of ways to be able to calculate the density based on temperature, the volume based on temperature, and the density of the product. So you're able to see exactly what that volume change would be. And that also goes towards your design liquid level. So that sort of helps you understand what your risk is and how high you can fill the tank based on a hot day and a cold day, right? These things can change, right? And you might think, geez, that's pretty nuts, but it does happen. So in chemicals, you have what's called a density correction factor based on, we typically like to bring everything back to 15 degrees in the chemical industry. So you'll see each product might have a density correction factor of, like, I believe ethanol is 0.007. I mean, there's different, and you'll do your calculations. Don't quote me on that. I have a horrible memory, but essentially you'll be able to say at temperature X, you have a certain volume, at a temperature Y, you have another volume, and you really have to take that into consideration. Sometimes we miss the boat on that one, and that's in the industry, not specifically to any specific area. It just happens, right? So material specifications, that's really important. There's a lot of things to consider here. So manufacturing limitations, and when I'm saying rolling capabilities, it's really the size of rollers that are available in the industry. So you'll have 8-foot courses. You can have 6-foot courses as well. It all depends on what's available, who's around. Transportation, so you can only transport so much with cost and doing it safely as well. So you have to consider that. Weight limits for the material manipulation, so you don't want to arrive with 1 million tons of metal. Otherwise, we just build it in a shop and bring it to site, which has happened, but it's not exactly the best solution. Chemical composition, so carbon content, so there's very specific requirements for that, and for obvious reasons. Physical and mechanical properties, so hardness, tensile strength, melting point, thermal conductivity, all of these things. And really it helps us with weldability, constructability, and obviously helps us avoid some of those issues with damage mechanisms. So basically, if you start right, on the right foot, you can maintain the asset for a long period of time. You can do it in a very cost conscientious way. And so this is part of that. It's very important. Internal, external pressure, typically limited to the roof plates. It's obviously atmospheric, so you're not expecting to have anything above that. Although we do have a room to play with that's in the code as well. So we always give ourselves as engineers a bit of help with that, right? So so here's the next one. So structural, and that's where a lot of people are like, oh my gosh, like there's a lot to it. So I'll just talk very quickly on that one. So you'll have these different structural codes. You have to consider that with the National Building Code, you've got to do these calculations, right? Live loads, dead loads, all of these things, seismic, wind. The code. So if you look at API 650, it does stipulate how you go about it, but there's also these codes you have to consider. And at the end of the day, we're engineers. So API says these are the minimum requirements, but we also have to, like I had mentioned before, it's always related to the code that's most applicable, which is the one that is going to be the most stringent. That's what you base it on. And the next one, you have Annex F, which is internal pressure, which would be greater than 18 kPa. Or external 1 inch of water. You have elevated temperatures where you have yield strength reduction factors. And basically all that says is there's certain things that you have to do if you want to go above 200 F. So that could be, thickness of your shell. Like there's many different things. So you have to consider that. So it depends on if you're doing it before this is a repair and you'd like to heat the tank. So there's various things you have to go through to do that. Annex 5, when you're considering greater than 0.25 kPa, there's certain things that you'll have to do there as well. Then when you look at product characteristics, specific gravity, which is very important, right? Storage temperature. So when you look at pour point, flash point, corrosivity, mixing required, Is it homogeneous? Does it remain that way? And when you heat, a lot of the times you like to make sure it's mixed so that you're actually getting that entire product heated. Vapor pressure. So when typically between 10 and 76.5 kPa requires a floating roof. That's normally how it's approached in the industry. So you can use a floating roof, you can use vapor recovery unit as well. And you also might think about a nitrogen blanket, right? Nitrogen blanket basically limits the amount of oxygen that enters in, or at least keeps it to a smaller content, sometimes under 3%. It all depends on what's required. So for biodiesel, for example, you might want to keep that underneath because it oxidizes. So when you're using fatty acid methyl ester, so something you try to start considering, right? So reactivity of the product. So a BLEVE, which is a boil over, all right, and it just continues going and there's not much you can do about it. Fire protection requirements and FPA and the Canadian National Fire Code, that's important to consider as well. So that's basically tank design in a nutshell. It's really just the basics. There's a lot to go through. When you go more in depth in that, you'll see more and more and you'll ask more and more questions. But we'll talk a little bit more as we go and hopefully give you a bit more of an understanding. Tank capacity, right? So diameter and height combination should be selected to meet the capacity required for the footprint and business case. So it's the best use of land, really. That's and what helps you make the profit. Height limitation based on diameter to height ratio for stability, right? So you can imagine if it's a very small diameter, a very high tank, or I should say high, let's say 70-foot height and 10 foot in diameter, you won't see that, right? For obvious reasons, it just won't be stable. You also have local regulations and permitting requirements. So they might limit you to a 40-foot or a 48-foot, right? So that's why it's very important to make sure that your permitting aligns with what you expect to build. Even when you repair it, you should be looking at and making sure that you follow your permitting and that everything works for that. Because if you do go to try to build a new tank, that's one thing that there'll be a lot of discussion surrounding that as well. And it's, again, access, right? So you don't want to climb 2,000 stairs to get up to the top of the tank. You can imagine, right? Mount Everest every time. So you got to think, there's a few things that you have to think about there, right? So, so tank levels. So as you can see, this is, for those of you who are really new with tanks, this is your tank shell, your floor, and your roof. So you have your top of shell height, design liquid level, which is what I was talking to you about before, your normal fill level, right? Which is where you would stop because you want to give yourself enough room to be able to manage or the risk of having an overfill, okay? Then you have your networking capacity and your minimum operating volume in the tank. So I don't want to go below my minimum level, right? So my pump can cavitate, right? So cavitation, as we all know, affects the pumps. That's not what you want to have happen. So as it draws air into the pump, you start to see cavitation happen. So we try to avoid that. And when you look at your normal fill level to your design liquid level, we have to consider expansion. We have to consider how fast that is going to be coming in. So typically it comes in through, let's say, a 12-inch line, right? So it might come in at 5 meters per second. Your flow rate might be anywhere between, high level 2,000 liters per minute for argument's sake. You need to be able to react fast enough to be able to shut that that valve, right? So you don't actually get to your design liquid level. So you'll have overfill protection as per API 2350, and they give you the calculations to be able to do that safely. Typically, you'll put alarms. You should have an alarm for your high level, high level, your low level, low level as well. So, and the minimum fill level is based on suction properties and MPSH. So net positive suction head. And it's also based on the lowest appurtenance in the tank. And what I mean by that is basically what's the lowest. So you might have, let's say, a manhole cover or an entry, I should say. You might have a mixer, these type of things. So you really want to give yourself a bit of room above that, maybe 2 inches above those, to be able to give you that lowest level if you have a floating roof. If you don't have a floating roof, you can go below that. So that should help you, right? So the types of tanks, again, here we have the roof. So you have a dome roof where the shape of the roof is based on spherical. So it's mainly spherical. Cone roof where it looks more like a triangle. You might say, well, why do we go from one to the other? There's various reasons. It could be constructability. It could be, you know, if you're putting you could put a dome roof on a external floating roof to protect it from the weather, these type of things. And then you've got internal floating roof where the roof floats on the product and it's protected by a fixed roof structure, really keeping the rain out. And that's also keeping the vapors in, right? So it's very important. That's the whole point, which is what I mentioned before, right? So if your vapor pressure is going to be such that it evaporates, the product evaporates, you want to make sure that you can stop that evaporation, stop it, volatile organic compounds going into the air. So that's the main reason why I use that. Other reasons in the past as well were product loss. So you could see over a month's time, as you had vaporization of the product, that you'd lose a fair amount of product, right? So that's other reasons for that. External floating roof, which basically does the same thing. So it's not covered by a fixed roof though, right? So the idea there is when they did the tests back in the 1920s, they showed that they were able to put out the fires. It was quite easy because you had direct access. So you'd have what's called rim seal fires, and they were able to put them out. It was quite interesting, and you could look more on the internet to see as you know, how they were doing that. But the idea is, you know, CB&I had done this testing. So we'll go to actually what I want to show you here. A bit of the tank structure itself. So this is your. I hope you can see my mouse. Let me know if you can't. But this is the foundation here. This is like a low clean out. On more heavier type of products, you might see that. Shell manway, you have your plates for the floor. You have your indicator for your levels. That might be a float or radar. You could have a fill pipe from the top or from the bottom. A lot more, it depends on the product, but most tanks fill from the bottom. Shell plates, roof manway, caged access and ladder. A lot of times now it's stairway. Roof manholes, a handrail, sorry, vent with a cage, so you'll have some venting for the tank as well. So it just kind of gives you an idea, the general idea of that. And here you see another idea of the tank and how all of the shell courses are offset so that you're not lining up all your shell courses horizontally in one area, that it just splits apart. So it actually helps it for strength, right? So internal floating roof. There's a lot of these in the industry. They vary across Canada and across the States as well. Different types of floating roofs for different areas, different companies, different preferences. A lot of times when we look at this, we want to look at, you know, how it can be supported, how people can in the area support that, right? So contractors or what have you would be able to help you with that without bringing people in from other parts of the world, because there is time, you know, there's schedule, there's money, all these different things that come into play. So basically, you have two that I've shown you that are typical. In the West, you'll see a lot more of these floating roofs. So like a honeycomb type of floating roof, which is basically like panels that have aluminum around them, and basically they sit right on top of the product. And then you have your hybrids. You have these as pontoons. They can be stainless steel or aluminum. You have your support structure that goes along here, your legs that support it. So when it's sitting down, it's supported. But mostly it's supposed to be held by the product. And the idea really is to limit the vapor space, right? So you could imagine without the IFR in there, you'll have issues. You'll have lots of vapor, and that you don't want to have for the environment, right? So you want to make sure you minimize those vapors. And you might say, well, geez, how does this stop that, right? So it's really forcing down on the product, right? So it's pushing down on the product, which limits the amount of vapor that the product's able to eject into the air. Now, it doesn't do it 100%. There's efficiency to it. There are some that are better than others. You can see here, you'll have a little bit more vapor space underneath, right? So you might have more vapors coming out from one of these type of roofs rather than the full contact. There's many vendors that do both. So you might want to have a look at that and try to understand that. But for all intents and purposes, these do meet the CCME requirements and the local environmental, depending on your, I guess, the province and where you are in the world. You could be in different countries and what have you, but typically these meet the requirements. So that's something you do need to look at and make sure that that's the case for where you are. So the other part is you can suspend them by cables, or you can use the legs. And you might say, well, what's the difference between both? Well, from an operations perspective, it's a heck of a lot easier. So why I say with cables is that what we're able to do is we'll have various heights that these are set to. And the reason for that is because you can imagine trying to do some work in here and there's a floating roof. Now, a lot of the times it'll be roughly 3 feet, right, high for your operations to be able to use and maximize the products, the space in the tank, the volume in the tank. So we'll have various levels. So we'll say, let's say 3 feet, and we might have 7 feet for maintenance position. What that allows us to do is get in the tank and actually do some work without bumping our heads everywhere. One of the things I'd like for everyone to understand is those of you who do work in the tanks is that obviously if you have a cone up or a cone down, that 3 feet is relative. So you might have 3 feet at the end and you might actually have 2 feet in the middle, right? Depending on how that cone up works and, after time, how that roof sits. But these are things to think about. So when you're setting your levels, you want to make sure that, relative to the lowest or the highest point, right? So we've banged lots of heads on these pontoons. So you just want to make sure in the industry that, hey, let's get them high enough so we're not banging our heads. The other thing to consider is fall protection. So because you are able to get on top of these roofs, they do support 500 pounds per square foot. That's what they're designed for. So you can have two grown people in one area. So they give you a bit of room, but something to consider is that when you're up on top of that you have to make sure that you're at least safe. You could imagine there's some skin here, what we call skin. It's really just aluminum sheeting, very thin, and these are your bracing that goes across. So that's what supports you. It's a similar concept here, except typically with the cables that helps support in the structure itself. Within the structure it supports that, right? So yeah, let's go to the next one. External floating roof can usually have double deck or pontoon type. So the biggest thing is, when you're looking at this, it all depends on what, a lot of times it's cost related, but to be able to say, hey, what's the best, like I was saying before, who's around, who's easy to be able to do maintenance on it. You can imagine this might be a little bit more difficult to do maintenance on. If you look at this, you just have these pontoons that are on the circumference. So these are much larger. There's a bit more inspection to do on these ones. You have to make sure they float, right? That's the whole idea. So if you're thinking about doing some sort of pressure test or liquid penetrant test, I find that these just are a little bit easier. So it's just something to think about, because you always want to think about maintainability, operability, and you want to make sure that as you're maintaining it, that it's easy to do the non-destructive examination, right? So something you might want to think about, right? And some of the advantages when you're looking at external versus internal is that I can get access on this. I don't have a closure here, so it's easier for me to see even from above what's going on with the tank. So I can look at the seals, I can look at the, essentially how that roof is reacting. Some of the negative parts of that is obviously you're gonna have to have a drain on the roof. You have to calculate that to be able to handle, I believe, 10 inches of water. So what you want to be able to do is make sure that drain works. You'll also have a check valve. So the water will accumulate on here, snow, ice, water. It goes into here, into a sump, and then out through the side, right? So there's a check valve so that if there's an issue with the piping inside the tank, that it doesn't come out on top of the roof. And the other thing is that the piping will connect directly to a valve, and which has a sensor in it. So it's built to be able to sense whether there's oil or not. And if there is, then you're not able to use that valve. It will either give you a warning, you'll see it, and you'll be able to shut it down, or you can have a warning that's in there as well. So there's various technologies you can use to mitigate that. And you can see here where these legs are, all the legs to support that, and these pads here are really welded on the tank floor to be able to protect that over time. It make a difference. The seal choice. So the seal choice is a big one. So you say, well, why do we need seals in the tank? Why don't we just put a big round plate in the tank that goes up and down with a little gasket, right? Well, tanks are not round. Not always. We think they're round. They look round, but if you really look at it, you'll see that it can be quite it could be quite interesting, the variances. So that's something to consider when you're doing your out of service inspection. You want to look at your tank roundness, and there's ways of doing that. But that's really important, especially if you have an IFR, right, or an EFR, right? That the roundness is so important. So what you do is you give yourself enough room to be able to put the mechanical seals in there, or whatever seals you decide to do. And those seals are really sealing around that tank, around the circumference, so that you're going to have movement with that going up and down, especially if you have columns. You know, these things move all the time. It's just the nature of it. You're sitting on fluid. That fluid, you know, you typically think of it as static. A lot of times it can move, and there's, you know, small, you know, vibrations on the planet that you know, everything moves, right? So there's changes in soils that you might not be able to detect that happens, right? So these things do happen. So yeah, that's something you want to consider. Typically you'll see mechanical shoe seals and wiper seals. That's just what I've seen in the industry. I've seen a lot of log, you know, vapor mounted seals of different types, but the main ones I've seen are really the mechanical and the wiper seals. You might have 2 wiper seals, you might have mechanical, you might have double mechanical as well. These things exist, and essentially all it is a stainless steel shoe that's being held in place by tension. You can have liquid or vapor mounted, as I said, in order to meet the future requirements. I like the mechanical with the wiper seal. It aligns with best practice. Double mechanical works. It does. There's a lot more to it, so it's something you want to consider given the cost and the time, right? So, so I was saying at the beginning, which is soil conditions and footprint. So what are we doing? Are we on a greenfield or a brownfield? That plays a lot into the decision on your tanks. But this is really the basics. Like, you need to start with something that can handle the tank, the weight of the tank, right? So soil compaction, permeability, load bearing capacity, right? So the biggest thing is you know, can the soil handle it, right? There's various ways of if you know, being able to measure that soil compaction and be able to tell you whether or not that's going to work. And if you look at a lot of the installations basically on docks across, you know, North America, a lot of it's fill, right, where they've tried to expand on the dock capacity and what have you. So you have to be careful. There's various lots of methods we looked at, you know, to be able to improve the soil compaction and so on. Permeability obviously is very important, right? So you want to make sure that if there is an issue that you can contain it. So you'll have bun walls, what's called bun walls, and basically all they do is your tank is put within. We'll talk about that later on. Load bearing capacity is what I was really trying to push here. So you can do preloading, vibration, material displacement to be able to make better soils. You can use you know, proper foundation. Obviously, is going to support the floor and shell. Corrosivity, which is mitigate the risk of bottom side metal loss, which is, you know, pH, right? That's a big part of that. Granularity of the soil, water content, and there's various others, but these are some of the main ones that I've seen. And basically, you know, if you can control the water under the tank, that's a really big way of being able to mitigate the risk of having an issue. There are more, but those are the usual ones. I'm going to move a bit quicker so we can have some Q&A. Tank foundations. These are the various tank foundations. So sand cushion, tank bottom, tank shell. You'll see some drain pipes, which what it does is basically able to tell you if there's an issue with this, right? So your primary containment. These are all from ABI 650, so you can have a look at that. Tank bottom construction. One big thing here is you can see how the plates are laid out, right? Everything's offset. The other thing you want to consider is when you look at these plates, how you weld them, right? So you want to weld maybe here, 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 do your long ones after, because you have expansion. So you'll have a compressive stress, tensile stress here, and you have compressive stresses here on this, let's say this weld here. This happens, and what happens is your tank floor can bulge and buckle as it shrinks, right? So you want to be careful with that. This is the various ways of which we're attaching the plates to the shell. That's the most important weld you'll see. We also, when we look at our tank shell, so we look at our loading. So as we go down here, you see the loading gets larger, just because you have more force pushing against that corner weld, right? So with the density of the product, okay? So you'll have variances in pressure that also from the vapor pressure going in and out of the tank. That's also going to be something you have to consider when you're looking at the weld up top and when you're looking at the stability of the tank and what it can handle. There are thickness considerations regarding constructability, right? So one of the things I've learned in my career, don't go, if you can, try not to go less than 5/16 on the shell, otherwise you're going to get warping, right? So you see each shell is going to be thinner than the next one as you go up. You align them so that if you do put a floating roof in here, that seal will go along here. You can imagine here you'll get caught up. So we hold, in the way we put these shells together is we use this device to hold it in place while we weld, right? That's the most important part. And then obviously you have to look at welding procedures, all of these other things that come to play. Shell to floor weld is what I was saying. This is that chime that comes, this is the exterior of the shell, of the tank. This is the internal part of the tank. These are your fillet, what are called fillet welds. And it tells you the various ways in which you do that. You try to give yourself enough floor projection. And the other thing is you'll see what's called lap welds on these. We'll go back to that. These are lap welded together, okay? So you want to make sure your laps are be able to support the shrinkage. So they say 2 inches. I try to give myself additional overlap because things happen. You know, depending on the heat and what you're doing. So there's some lessons learned from that. Miscellaneous tank components, so pressure vacuum vents used to allow outbreathing from vapor pressure, product inlet displacement. So basically all that happens is you'll see here, right? So you can see there's weights. There's other ways that it can happen. There's can be springs or weights, but essentially what it is it pulls in through here, goes into this chamber, goes in, right? So this weight will be designed as per API 2000, which allows that calculation for what speeds you're expected to have that go in. And then you're outbreathing what's expected. And really why you want to do this is for mainly the fixed roof tank, obviously for fixed roof tanks, but you want to minimize the vaporization, right? So that's a way of doing it. We have sometimes what's called goosenecks where these are removed. And if you have an IFR, that's typically the way you go. This is a gauge hatch. There's what's called a strike point on this. And basically what you do is when you're gauging a tank, people talk about what's it gauging a tank? But it's really taking a measurement of how much volume is in that tank. And you have what's called a strapping table, which is calibrated to that specific tank and that specific volume that you're looking at. And you have to find a way to be able to relate the two. So what it does is it tells you per inch or per millimeter or per centimeter, essentially how much volume there is. And what you'll do is you'll measure what's called either outage or you'll measure innage. Outage is really what's measuring from the top of the tank, going into your strapping table and saying, okay, I have, let's say 7 feet from the top to the bottom where I'm touching the product. I'll go on the strapping table at 7 feet, it gives me the volume, right? So, and then, you know, things to consider is like, okay, so how would I get that into, some people like to talk in kilograms. Well, then you have to consider your density and the volume, right? So these are some of the calculations you might do. Typically strapping tables are going to just show you the volume. So, you know, something to think about. Common tank problems, so bottom side corrosion from excess water ingress on tank bottom. So that happens. Buckling and bulging on the shell, that happens with sometimes has in the heat affected zones. A lot of the times that'll happen. Sediment problems from porous soils and foundations. This typically causes edge sediment, planar tilt. And basically there's what they tried to do is put all the sediment. So you could imagine how edge sediment is sort of where that corner well is and how it might sit down versus the rest of the tank, and that puts stress on that corner weld. So you want to look out for that. Uniform settlement, you want to look out for that because of your piping that's connected. Remember, you're connecting piping to the tank, and you'll put stress on the shell if you do have issues, right? You'll have tilting, which means basically the tank's not sitting exactly where it should be, right? It'll be offset. You can have twisting as well. There's various things that can happen. And it's basically what they do is they've done a lot of studies and they've put together something that is the easiest for us to be able to calculate and talk about. In the API 653 code, which is basically you have API 650 and then API 653, which talks to or speaks to the inspection side, the repairs, and it oftentimes refers back to 650. IFR issues with pontoons and seals. So pontoons, so biggest things with those is basically issues with welding, What happens there is we'll test them. You can pressurize them, or you can do liquid penetrant tests, and you'll see there. You want to make sure it floats, so those have to be repaired. Seals, I've seen in my career where there's been issues with seals over time. Remember IFRs, how long they're supposed to live for? A lot of times the manufacturer will say 20 years, so keep that in mind when you're doing your inspection. You also have, leg issues, floor denting, all of these things from leg impingement. So one of the things to consider is how you're floating that IFR, how you're landing that IFR. You have to consider that speed of what you're doing, and we always have a rule of thumb in the industry, 1 meter per second. So whenever you should never. So when we design these IFRs and EFRs, they're not supposed to be landing all the time. They're supposed to land when you're doing maintenance and repair. They're supposed to land when you're doing, let's say, RVP changes, these type of things, right? Or if you have real issues, right? But they're not supposed to be landed all the time. And so we need to make sure that everybody in the industry understands that, no, we have to give ourselves a safe area where we're not landing these legs. They're, because you can imagine with cables, not an issue, right? But with legs, yeah, that's an issue. So we don't want to be doing that, right? Coding issues that I've seen internally, externally, that's been industry wide. So we need to make sure, and when you have coding on the internal side of things, you have to make sure that it's inspected by an ACE. You have to make sure that it's done correctly. You have the right humidity, levels of humidity, and so on. So really make sure of that. One of the biggest things I want to make sure that everybody understands, for those who are doing tank work and understand the coding, you should look at the holiday tests, right? You should talk to the vendor and see, because obviously with a holiday test, you can damage the coating, but you need to make sure you can find the holidays, and visually it can be difficult, right? So something you want to think of. The other thing I want to make sure everyone knows who are doing tank work, when you're in the tank and you see the floor, make sure you think about vacuum boxing on your lap welds on that floor. You're in the tank, you want to make sure it lasts a long time. What's the cost? What's the issue, right? Like, we should be doing that, right? Things happen. Welds might have been done a long time ago. They don't follow necessarily what we would follow today. So I'd like to make sure that people consider that at least, right? So inspection requirements and mitigation. So we have magnetic flux leakage, which is basically how we're able to take a volumetric loss on our floor based on how that metal is reacting. We're able to see that volumetric loss. And then we'll follow it up by phased array or ultrasonic thickness readings, spot readings. And the reason for that is to really get a more qualitative and a quantitative, right? So we want to follow up with that. And that's how we get our corrosion rate. And we say, hey, how long did this take and how much did we lose based on what was given to us at the beginning, right? So with that, we're able to say, okay, well, the tank floor. And everyone says, you know what? That's the tank floor. That's going to make this tank last long. If we fix the tank floor, this tank's going to last forever. No, that's not the case. That's only part of the story, right? So remember, especially if you have an IFR or an EFR, there could be a lot of other things that limit that. So for example, in those IFRs, when you have around your columns, if you have columns, because you can have tanks without columns, but you look around the ceiling around those, you want to make sure you change those if you're in there. You want it to last long, and typically the vendor will say 7 to 10 years, right? So, and if you're going for 20, well, that's something you have to consider. And I think there was a comment in there. I saw that those IFRs usually last longer. Yes, that is the case. They do usually last longer. But if you botch it up and you don't inspect it correctly, you're going to have an issue. And I've seen it in the industry where we've said, we're good to go, and not the right things were done. So it's oftentimes very difficult to go back in once there's an issue, especially if the IFR sank. So yeah, that's not fun. As I was saying, vacuum box, liquid penetrant, penetrating oil test for corner welds, visual inspection, tank shell, visual, magnetic UT crawler, tank roof, visual, UT rafter inspection is often missed. So typically, tank roof, I'd say visual before you get on it. You got to make sure that you're safe, right? That there's nothing. So where you'll run into issues is where it's insulated, and that's an issue. So what you might want to do is pulse eddy current, and you'll be able to go through and be able to see what the thickness is on there. So hopefully I shared something for safety for someone that might think about doing something like that. Rafter inspection is very important, and typically we look 48 feet in the air and we're like, yeah, it's good to go. But consider robotic, right? Have a look at it, right? And be able to go in that rafter. And the other option is you can do from the top, you can make some cutouts and be able to inspect the rafters up there as well, right? Some things you want to check is the frangible joint. And what I mean by that is there's a joint on the top of the roof, which is designed so that if there's an issue with, let's say, fire or anything happens, you don't want that tank to fly up in the air. So you'll make that weld sort of a very thin weld. It won't be very strong, but strong enough to hold with the vapor pressure and what have you. But if it overcomes that, then it will pop up top, right? Which is what we strongly suggest you have. And the IFR, EFR, it's basically you want to make sure it floats and it stays floating and it handles those, it keeps those vapors from going out. That's the biggest point of that. So mitigation measures, cathodic protection, vapor corrosion inhibitors, very important. It's good engineering practice. Topsoil selection of coating would help to, for the top side, sorry. So if you're starting to think of storing FAME, fatty acid methyl ester, well, you should be thinking about coating, right? So it helps you from MIC, right? Microbiologically induced corrosion. So that's something you want to think about, right? You're looking at the shell stress, focus on foundation support, integrity, operating windows, tank cycling, and corrosion. So I mentioned, like, watch your tank cycling. Make sure that you're not, cycling that thing every day. That brings your risk up, right? So you want to make sure that you're operating within proper integrity operating windows. So again, thinking about the whole idea of renewable fuels, ethanol, stress corrosion cracking. So you want to make sure you're coating that, right? At least for the bottom 3 feet. That's very important. That's where you'll get most of the stresses. So that's some of the things that we like to think about. So that being said, I believe that's it because I wanted to leave some time for some questions.
No, that's awesome, Tim. I appreciate that. That was a really good presentation. I know we have a limited amount of time here for questions, but enough time to kind of get started on here. So maybe I'll kick things off here. So you briefly touched a little bit on this with some of the talk about working up at heights, but what do you find is one of the biggest safety risks when constructing or inspecting tanks? And then how would you go about to mitigate that?
So the biggest risk obviously is confined space, right? So you want to make sure that if you are with confined space, you have to make sure that you're doing the proper permitting process, you're doing a proper risk mitigation even before you're thinking about it. And one of the things I like to do and make sure happens is industrial hygienist, right? You want to make sure that you're not exposing anyone to any type of toxins, hazards. A lot of times we don't know what's actually in the industry, what has been stored there. So if you're dealing with a tank that has already been in service for many years, you might have lead, for example, right? So these are the type of things you might think about as well. Mitigating that is obviously, proper gas detection, making sure you have the proper training, harnessing. You need to make sure that you have a plan, right? So you have to have some sort of plan that shows that how you're going to be rescued, what that situation is going to look like. All of this stuff has to be discussed long before you even consider going into the tank. That would be the way I would approach that.
You called it an industry hygienist on that to go and see what's been in there? Like, how do you know if there's been lead or other old materials on there that you currently aren't storing there?
Yeah, so basically an industrial hygienist, the first thing they're going to do is they'll take a 5 gas detector, they'll go in there and they'll look for, they'll test VOCs from the exterior. They'll be able to give you an indication of that. They'll take historical documentation. They'll try to look through as much material as they can. And they can do swabbing, right? So swabbing, they can send that to a lab. So they'll be under full respiratory equipment before they even get in there. They'll be able to take some swabs. They'll look around the tank. They'll be able to do some testing. If you're looking at pontoons, well, you're going to be, the pontoons are designed to be tested. So you'll be able to do some testing in there as well. So, yeah.
That's cool. Maybe move on to the next question here. So when you are looking to clean a tank, you need to typically estimate, what does the project cost and what are the work requires? And often that's based on things like historical information, often minimal data, or sometimes, samples from one of the sample lines. So maybe from your history, how often do you find you get budget overruns, and then how often, or schedule extensions and such?
Well, in the industry, it happens. And the reason why is because there's not a lot of documentation in the past. So, and again, it all depends on the situation. If it's an IFR, if it's an EFR, if it's fixed roof, a floating roof, well, as I just mentioned, floating roof. So what you typically like, it's difficult to say because the biggest part of that is making sure it's safe to go in, right? So it's making sure your LELs are at 0, and that takes time. So it's based on, you could look at tanks in similar, so you could reach out in the industry and ask other people who have cleaned similar products, because if I'm talking about asphalt or I'm talking about ethanol, it's two different things. Ethanol, no, I never go over. That'll never happen, right? So because the thing about that is it's much easier to get off the wall, it's much easier to get safely, where asphalt, you know, if it's not hot, solid, and it's very difficult to remove. So these are some of the things you take into consideration. Yeah, that's, I typically go and I ask in the industry, or I've seen it, and I try to do that, you know.
Okay, so fair enough. So usually it can be often easy to predict, at least for nice ethanol tanks, but not always all the time.
Yeah, not all the time. So lighters are a bit easier, but when you get into more of the heavier products, it can be, you know, it could be very difficult.
So maybe time here for one last question on here. So what is it, what is the
Sure.
difference between single walled and double walled tank selection? Why might you use one over the other?
Well, I wouldn't build a 100-foot diameter double walled tank. It would probably cost me too much. It would be a bit overkill. So typically we'll look at the smaller horizontal tanks. They'll be double walled. Some of the smaller vertical tanks you'll see that are double walled. And basically what we see in the industry is that as long as you're in you have everything else, all your protective measures, you put in corrosion alarms on your metal, you put it in an area that's decked properly that can contain your product. You have a lot of other risk mitigation measures that are in place that suffice. So that would be how I would approach it. I'd be like, well, because a double wall tank, as you know, you have interstitial space that can be tested, so you have a good understanding. But what people forget about is that first part of the shell, right? Is it's very difficult to be able to see if that's leaking or if there's another issue, right? So there's pros and cons, as there is any. Yeah.
Okay. No, awesome. No, I appreciate that. So unfortunately, that's all the time we have today for the Q&A. Thanks for all the great participation out there. We had some really good questions on it. Tim, would you be open to have anybody reach out if they have anything else addition with any extra questions based off of your talk?
Yeah, and in fact, I don't know everything about anything. Like I'm learning as everybody else is, and I would be so happy to reach out and have a whole chat about all of this. So I would certainly appreciate that, and the feedback, right? So there's different people who have different opinions and different ways of looking at things, and that's one thing I've learned in this business, is that there's not one way of doing something. There's a lot of different ones. If you're not open, we can't discuss, and I can't share, then we're never going to get better as an industry. And so that's the whole point for me, is really helping the industry get better.
Yeah, I couldn't have said it any better. Well, thank you. I really, really appreciate you taking the time to put this together. I think it was a really informative talk, and I know I certainly learned a lot. So it was very well appreciated. So with that, I'm going to close out with that. Be sure to follow us on LinkedIn for our next upcoming webinar. We actually have one in 2 weeks on May 28th, and we're going to be hosting Roy Christensen, who's going to do a talk on third-party vendor work and whatnot. So keep a watch out on LinkedIn on that, and we'll be able to post that. So with that, thanks again, Tim. It was great hosting you. And to everybody else, have a wonderful weekend. I appreciate it. Bye.
Thank you. Take care.